In Bayesian parameter estimation, we make use of conditional probabilities. And we went through conditional probabilities using two variables, and in that case it was two discrete variables, one variable with four possible values, A, B, C, D, and another variable with two possible values, yellow and blue. And what's important in this case is that if you add these probabilities here, 0.4 times plus 0.3 plus 0.2 plus 0.1, that adds to 1. Now, if you add all the yellows, 0.10 plus 0.10 plus 0.10 plus 0.05 equals 0.35. If you add all the blues, 0.3 times plus 0.2 plus 0.1 plus 0.05, that's 0.65. And if we add 0.35 and 0.65 must add to 1. And if we add the 8 values in internal values, and it also adds to 1. Now, with continuous variables is much more complex. So let's say instead of the values that we assign for the discrete distribution that we assigned arbitrarily, we can use a distribution to assign those values. In this case, it's a normal distribution, but sometimes we can use a continuous distribution, like all the values are equally plausible. And then again, when we go to determine the probabilities in this space, in this continuous space of two variables, well, it's not as easy as in the discrete distribution that we assign probability to two partitions, two possible values. Here we need to assign probability to a continuous distribution to a continuous variable. It's like having normal distributions, so all these are normal distributions for each value of the variable in the x-axis. Now, each value is their infinite number of values, so it becomes computationally very, very complex. So we cannot do as it did in the discrete distributions, is that we can determine those values by simply observing the values in a grid. Here we've got infinite number of values and it's not possible, but the rationale is the same. If we add all these values, this should add to 1. If we add all these probabilities, it adds to 1. And if we add all these probabilities, it adds to 1. And these probabilities are determined by the sum of these probabilities. Now, it becomes very complex in continuous distributions, but it follows the same rationale as in the other distributions. Now, this is conditional probability. Bayesian estimation uses the Bayes theorem. So here is the Bayes theorem, and also the Bayes theorem has a version as discrete variable and a version as a continuous variable. So this is the version of the discrete value. So in the case that we were interested in, let's say we consider this probability. The probability that a drone landed in a blue area, given that we know that it landed in area A. So if we go back, we know that it landed in area A. This is the data we have, and I hypothesize about whether it landed in yellow or in blue. And basically we want to know what's the probability that it landed in blue. Okay, so as I said, here we can determine that almost by visually, but otherwise we just do 0.3 divided by 0.3 plus 0.1, which is 0.4, and that's 0.75. So we do it very easily, but how do we do it in the continuous space? Well, we cannot do it in the same way. But let's examine the Bayes theorem. We can use the Bayes theorem to approximate that calculation. Now, the Bayes theorem is going to do, in the discrete case, the same. It will produce the same outcome as what we can do by observing the values here. But I just want to show you that in order to justify that we can do the same in the continuous case. So the Bayes theorem has what we call the posterior distribution, which is what we are interested in. What's the probability that x equals blue, given that we know, what's the probability that y equals blue, given that we know that x equals a? Well, that is given by the opposite conditional probability, which is probability of x equals y, given y is blue. So what's the probability that the drone lands in A, given that we know it landed in blue? That's called the likelihood. And that is multiplied by the prior. The prior is what's the probability that the drone landed in blue. So that's not a conditional probability. And finally, that's divided by probability of x landing in A. That's called the marginal likelihood, or the probability of the data. Now, if now we can replace what's the probability of landing in A, given that landed in blue? Well, probability of landing in blue is 0.65. Probability of landing in A for blues is 0.30. So the probability that we're looking at is 0.30 divided by 0.65. So that's what I replaced there. What's the probability of landing in blue? 0.65. We get it by here. And what's the probability of landing in A is 0.40. We get it here. So if we do this calculation, the result is 0.75. And you may say, why do we do this complex Bayes theorem when we know that much easier? We can calculate that very simply by observing the values here. Well, because in the continuous case, this is not possible, and we don't have visually the values, and then we need this theorem. Okay, so look in the continuous example. I use probability of y given x, and that's a shortcut for what's the probability of observing a value, any value of the variable y, given that I observe specific value of x. And that's given by this theorem. Probability of x given y, which is what's the probability of observing the observed value of x given any value of y, and times, so that's called the likelihood. And that is multiplied by the prior, which is the probability of observing any value of y. So probability of observing y is given by here, by this distribution, this normal distribution there. And then P P of X, probability of X, is the marginal likelihood of, or the probability of the data. And if we go there, instead of going up, I've got the graph here. It's coming. Now, so this is the general form of the Bayes theorem, and we can replace y and x by the things that we want to estimate in this case. So instead of y, we use beta 0, which is the coefficient we are interested in for the estimation, which is, as you know, the mean in this case, but it's not always the mean. And beta, this is B0. B0 is the calculation that we do of the mean in our sample. So that's why it's replaced by y bar, which is the mean of our sample. And we do the replacements here as well. So basically this is the posterior, and this is the likelihood. This one is the prior, and this one is the probability of the data, or marginal likelihood. Okay, so that's probability of B0 given that beta 0 was observed, a specific value of beta 0 was observed, times the probability, sorry, I come back to the likelihood. The probability of observing a specific value of B0, which is the one we observe in our sample, given any possible value of beta 0. That's multiplied by the prior probability of beta 0, and that is divided by the probability of B0, which is the probability of observing the value we observe in our data, in our sample. Okay, so that is represented here. So we've got beta 0 here in the x-axis. We got a B0, or the mean of the sample we obtain, in the y-axis. And this one, we use a continuous uniform distribution in this case as the prior. So instead of using a normal, we use a continuous. And by doing that is that we assign a equal probability to the all the possible values between 0 and 100. Okay, then we use the likelihood. The likelihood, I show it in a different graph because it's the way we construct this is, if the value of beta 0 is this one, let's say 0.1, then this is the probability of observing the different values of B0 in a sample. If beta 0 equals 0.5, it's shouldn't be here. It's here is around 0.7. So we look at there, and well, what is the probability of observing different values of B0 in our sample? If it is 0.4, this normal distribution gives us the probability of observing the B0s in our sample. Now, we've got these distributions here and the prior here, and the formula tells us that we need to multiply the likelihood and the prior. So by multiplying these values with these values, we obtain these new values here. Right, and Now, the third part of the equation is the probability of the data. Okay, so basically we collect the data, we calculate the mean in our sample, and it corresponds to one of these lines. Okay, how do we calculate the probability of the data? Well, we add all these values that are in this row. By adding all these values, we obtain the probability of the data. Now, we don't add because these are continuous distributions, and are not only one continuous distribution, is the combination of more than one continuous distribution, or actually two continuous distributions. So we integrate, we don't add. I said add in order to make it easier, but we are going to have an integration there. And finally, we obtain the posterior distribution by having those values there, considering those values over there. And those values over there have to be divided by the probability of the data as indicated in the Bayes theorem formula. And that gives us the posterior distribution. Now, why we go through all this trouble? Well, remember that what I said, that I was uncomfortable with the traditional method. We use the data to determine the probability distribution of the population. And then we use the probability distribution of the population that we estimated from the data to determine the probability of the data. So it's a bit circular. In this case, the prior distribution, which is here, we provided that before observing the data. Now, isn't that a bit subjective? Well, in a sense it is, but we cannot choose this freely. We need to justify. Why do we use a uniform distribution? So, and this is a debate, what prior distribution to choose. Sometimes we choose one that is uninformative, like the uniform distribution here. It doesn't inform, it doesn't give any preference to any values. But sometimes we can use, for example, a normal distribution with a center in some value, and that comes from previous studies. I conducted previous studies, or other researchers conducted previous studies, and the mean of the that calculated in those studies tends to be in a range, in a particular range. So I can use that information to provide my prior. So when I do the estimation, it's not an estimation that comes from zero, but it adds the knowledge acquired by previous research. So my new posterior distribution is a update of the knowledge acquired by previous research based on my new study. So instead of using the study, this individual study, as to make a decision about the parameters of the population, I can combine this study with previous studies